Welcome to Machine Learning Fundamental Week 1. And yeah, so, okay. Yeah, so first of all, here's the content for today. Since this is our first session, we'll first do an introduction on the about UTMIST and this program. And secondly, we'll do some small introductions on machine learning, just to, like, if you're new to the field, we're just giving you an idea on what it is, and then some applications of it, and then why you're probably want to learn it. And third, we'll do linear regression. If you don't know, it's probably the easiest machine learning model, which is the first thing in machine learning you will learn. So it's very exciting. So yeah, so let's do some introductions for the UTMIST and the program. So first of all, what is UTMIST? UTMIST is largest undergrad machine learning or AI club in North America. And we have 8 departments. I think that's we have more than 8 now. Yeah, okay, we have more than 8, but we have 24 plus design teams, lots of members, and yeah. And our goal is to help students to with different backgrounds to gain experience and then grow and develop in their professional and academic career in AI and ML. So yeah. So I guess more about this program. Actually, this. Yeah, so more about this program. What is Machine Learning Fundamentals, or MLF? So it's a beginner-friendly program that gives you the chance to learn about ML and also build projects through hands-on experience and to apply what you learn. And also you can meet people, whether they're from UTMIST or just people who are interested in ML, you can meet them. And so the timeline of this program, this is an annual program, so it runs from today all the way till March 2026, which is the mid or late winter semester. So the program is broken down into 2 parts, or 2 phases. So for the first phase, which is this semester, we'll be learning, we'll be like primarily learning through workshops, and then we'll do some coding exercises and stuff. So yeah, so that's like for the first half. And then for the second half, you'll have the chance to pitch your own project and build it with like a small group of people. Yeah, and then you'll receive guidance from people from UTMIST. If you have like any questions or difficulties or just need some mentorships on your project, then this is the right program. Okay, so I guess just about the first phase of content. So today we'll do introduction and linear regression, as we said. Second week we'll do logistic regression. Fourth week we'll do neural networks. As you probably know, neural networks is a pretty big topic, so we divide it into 2 parts. But it's very important in machine learning. So yeah, 5th week we'll do decision tree. 6th week we'll do naive Bayes and connections to generative AI. So hopefully that's something sounds more interesting to you. And the 7th week we'll do ML best practices, which is some like just some, I don't know, like industrial standards or whatever for like just do machine learning in general, and then like how do you develop models and then like cycles and all those stuff. And for the last week, we'll do some introduction to deep learning and more than machine learning. So I guess that's probably the most exciting topic. So hopefully you'll still until week 8. Yeah, so here's the second phase of content. Still like how it works is we're still like kind of determining it. But the key idea here is that you'll first see some project demo, which will have people to do some small scale projects, or maybe people from engineering department to introduce their projects. And then you'll have the chance to propose your own projects with a group of people, and you'll gain feedbacks from us. So how it works is you'll submit a proposal, and then we'll give you feedbacks on the scope and the difficulty and all the stuff of the project. And for the last part, if we approve it, then you'll have the chance to like implement it in like around 2 months or something. So very exciting. Yeah, so you might ask, why do you want to attend this program? So first of all, it's a very good way for you to get a head start in machine learning because as you probably know, if you're in CS or Eng, you probably won't learn machine learning until cert year, which U of T only offers courses in cert year about machine learning, which is very unfortunate. But with this program, you'll kind of learn the very similar content to all those cert year courses, and then you can get ahead in your machine learning journey. And also you can meet people, right? So look at the people around you. Those are people who are all shares the same interests with you. And then this program provides a very good opportunity for you to meet those people. And then you guys can become friends and then probably build something together in the future too. And also, this program is designed to help you learn beyond theory. So what it means is that, well, learning theory is kind of like the first step, right? But in the end, your goal is to make something work and then actually implement it. So, well, through this program, especially the second phase, you will have the chance to make that happen, which is very cool. And in the end, I guess probably most exciting stuff to you guys is that engineering project will, I wouldn't say prefer, but they will like values people who attend the MLF because they show good commitment and then they're sure about your knowledge after attending MLF. So yeah, so like you'll have a better shot at future engineering projects. That's something interesting. So what do you need to succeed in MLF? It's actually very simple. So first of all, passion, right? So probably heard like you just need to learn. If you want to learn something, passion is the best way to like gives you motivation and always. So hopefully you're all, I mean, you guys are all here, so I suppose you have like very high passion anyways. And also consistent attendance. So because we're introducing different topics over the weeks, and all those topics are very important and fundamentals in machine learning world. So I hope like consistent attendance is something that we'll see, and it will actually help you learn because machine learning is a very, very big topic, and you can't just learn something like everything in a week. You need to learn little by little. So like attending each week is a good way to keep track of your progress, and then you're like keep yourself accountable. And cert, so complete tasks. So we'll have some small exercises for you to do at home. So those are not hard, and it just gives you a chance to practice what you learn. And yeah, so that's just to make sure like you understand what you learn. And fourth, ask questions. So machine learning can sometimes get very complicated, especially if you're first year or second year. So worst year, or even your professor is still hard. But yeah, so just don't be afraid to ask questions because like asking questions is how you learn things. And we're all very happy to answer like whatever question you have to our best knowledge. And five is learn from your peers. So yeah, like here everyone is in their rooms. I believe everyone has something to learn from each other. So yeah, if you're having questions, you can also discuss among a small group of people or stuff. And so you guys can learn and grow together and then also be friends or something. And technical stuff, which is probably what your more cares about. But so we do need some knowledge about Python programming, hopefully, so you know how to write a loop or functions or conditional statement like if, else, if stuff. If you don't, I think I suggest you to like look at it or like learn just Python in like the next week or so, so you wouldn't get really lost at our programming part. And those topics are generally not hard. So even if you don't have like programming experience, you can like learn how to write a loop or a function in like a week. So yeah, so that shouldn't be a problem. And in terms of math, which is probably what all of you are more worried about. So for this program, it only needs high school math. So I guess you guys are all graduated from high school because you're here. So you should know derivatives and chain rules and stuff. We'll also be using a little bit of linear algebra about matrix multiplication. I don't think we're going to do more than matrix multiplication, but so if you're like first year, you're probably learning linear algebra anyways. So by the time we need to use it, you should be good to go. Yeah. Okay, so meet the team. Yeah. Does all the directors who are here wants to make introductions themselves? You don't? Because I don't know about people here.
Sure.
Yeah. We can just go around. Caden.
Can you hear me? Yo, so I'm Oscar, academic director. A lot of things that I do, ability, understanding what the journal that does, field, research that I'm mainly interested in. I'll also be your director for personally teaching your dynamics portion. So nice to meet you all.
Hi, so I'm Ward. You might have seen me at the club fair as well. I actually recognize some of the faces here. So yeah, along with Aaron, I'm one of the me and Aaron, we're the program directors. So we kind of oversee the delivery of like all the content that's being, I guess, taught to you. And all of those like smaller panels down there, right? Those are gonna be the instructors. So essentially the instructors of the program are going to rotate because of course each one of us we specialize in different parts of machine learning. So yeah, for every week you might see a different instructor, but don't worry, all the instructors are very knowledgeable in the topics that they're teaching. But yeah, do you guys want to like introduce yourselves as well?
Yeah, of course.
I'll go. Hi, I'm Caden. I'm VP Academics. So what that means, I guess, in the context of MLF is like setting the vision, handling like interdepartmental things, so like collaborating with technical writing folks. And yeah, but just cool stuff. Kind of what that things.
And I think the directors are important because it's really good for networking. Like a lot of the directors here have worked at pretty big companies. Um, for example, Kaden worked at BMO, or like one of our other directors, Andrew, he worked at NVIDIA. So if you really want to get your industrial insights, this is probably a pretty good source as well for like networking. And I feel like networking is really gonna help you in the future. I know like a lot of you have just started university, but trust me, it's gonna pay off long term.
Chloe, do you want to introduce yourself?
My name is Chloe. I'm academic directors. I work for Flex Workshops. And so I work with the education account. So I'm also
Yeah. Yeah, let me introduce the rest of people as well before I do a formal introduction of myself, which I realized I didn't do. So you see Warwick, Caden, Oscar, Andrew, he's fourth year Eng side. He works at NVIDIA. And I guess his interest is more about like RL stuff. So if you're interested in reinforcement learning, you can talk to him. Jessica, she's also the co-VP academics with Caden, and she's fourth year CS, and her interest is also reinforcement learning. Riyadh, I think he's also fourth year CS, and I'm not sure about his interest, but you'll see him like next week since he'll do logistic regression. Chloe is in Matthew, he's also fourth year MSci. His interest is about like responsible AI, yeah. So Matthew will have a series of workshops later in the year. So if that's something that interests you, you can also attend those workshops. And Jingming, I'm not sure which year he's in, but he's the instructor for the upcoming RL workshops. So you're very welcome to attend that as well. And I guess coming back to me, my name's Aaron. I'm a third year ECE. And primarily for ML, I work on natural language processing and their applications about LLMs. So if that's something that interests you, you can talk to me. Okay. So I guess we can do a little icebreaker just before we get started officially about the contents and stuff. So you should turn to the people on your left and right, and then so those will be the people who are hopefully learning with you through this program. And you just want to do like a short introduction of yourself, your year, your program, and why you're interested in machine learning or AI, and what's your favorite ice cream flavor. So yeah, I'll give you like everyone like 2 minutes to do that. Just talk to people. Yeah. That's fine. But come together once we get to the next part. Yeah. Wait, Hayden, you gotta mute the mic.
Am I doing?
How do you mute? No, mute the Zoom, mute the Zoom.
You need the Zoom.
Yeah. Oh, it's muted. You guys continue? Okay, come back, guys. You cannot see the full screen. Can you see the right now? Cadence, is there a screen all right? Is the screen all right? On to. The door man. Is that okay? Wait, what should I do? Is it? Oh, okay. Share? Oh. Huh? What? They say like follow along. Oh, yeah. So for the online people, if you guys can't really see the full screen right now, you can use the link I sent and then just to follow along on your screen. So we don't know what's going on with the cutoffs, but yeah, so, but anyways, we'll continue. So yeah, but it's great to see you guys like talk to each other and so passionate about stuff. Okay, guys, can we stop talking for right now and then we'll just continue. So, and you guys are happy, like, you guys should be chatting afterward. So good. Okay, so second, we'll do some introduction to machine learning. So, and their application. So hopefully it gives you a better idea about what machine learning is if you have no idea what it is. So first of all, what is machine learning? Does anyone has any idea of what it is? Raise your hand. Something.
Yep. Kind of like just teaching a machine to like process things and stuff like that, right? Understand being like we're not talking.
Yeah, so get a summary of it.
Yeah, that's
Anyone?
basically a general summary.
Mhm.
How do you teach machine?
Yeah, so
Yeah, so he said teaching machines to learn what kinds of data.
yeah, so that's pretty much it, actually. Machine learning is just study of lots of data and study the patterns behind it. So like, or what we call the underlying distribution of the data. So yeah. And maybe sometimes you'll need to eventually reproduce them, but for most cases you don't. You just need to know what it is. And so you might ask, then why don't we just use traditional like programming, like the function I showed on the screen is called, let's check if a number is odd, right? So why don't we just use something like this? Does anyone know?
It's like impossible to, it's like, it's like these.
Yeah, so she said just lots of time it's really hard to code up stuff case by case in the context of machine learning, which is true, very true. Anyone else?
We go into like bigger data sets, for example, like process images, and it's not as easy to actually use traditional programming to okay.
Yeah, so he said when we're doing things with like larger data sets like images, it's really difficult to do the traditional do things in like traditional programming way, which is also true. So here's just like how ML differs from traditional programming. So for traditional programming, which hopefully lots of you are already familiar with, is that you handcraft your logics, right? So you write an if-else statement and then you roll the condition yourself. So what it does is it does provide very high transparency, right? Because you know exactly what can be evaluated as true or false in this case. And the issue though is that it's really hard to handle like very large and complex problems. If you have like 1 million rules, are you gonna write like 1 million if-else conditions? That's probably not like what you want to do. And for machine learning, so there's no clear logics, right? But the patterns are derived from data. So as we said, it's the study about data, and you don't need to really like explicitly know what's the pattern under the data, but you have a model that learns it. So machine learning has mostly like kind of low transparency because you don't really know what's the pattern, as we said, behind the data. And your model knows it, but you kind of don't know what the model is doing, especially it's growing large. But the good thing is that it works, right? And it's easier to adapt to very large and complex problems like image classification or something like that, which it's kind of hard to do for just using traditional programming. So yeah. And probably just going through the image is kind of like for traditional programming, you have data and programs going in, right? And then you have to do a bunch of sequence computation, and then you get a result, which like in this case, it can be just if the number is odd or even, right? But for machine learning, what you do is that you give the model data and results, and you try to learn kind of the correlation between them or something, and you get a program or like which is a model, and then that kind of does the job for you. Hopefully that makes sense. Yeah, so application of machine learning. I don't think I need to emphasize on this because it's pretty much everywhere, right? Finance, robotics, ChatGPT, which you use, social media algorithms, healthcare, self-driving cars, spam email detections, and there's just way too many to name, but you already have a good idea of like, it can pretty much be applied to everywhere. And so we're gonna do some introductions on some major fields of machine learning. So we have computer vision, natural language processing, reinforcement learning, and generative AI, which is we're gonna introduce for today. So for computer vision just deals what the computer sees. So some problems can be image classification, object detection, face recognition, right? So an example would be, oh, it's like I show you an image. Can you tell me if the image is a cat image or a dog image? And also, just showing as you can see on the left, the image is a object detection problem. So you can see we're giving an image, we're kind of trying to detect, oh, there's a bunch of person or a bunch of people, and there's some cars, right? And you also see some bicycles. So you try to detect what objects are there in the image. So yeah, that's one of the fields, and I think Chloe is working on it. So if that's something interesting, you can talk to her. And natural language processing. So natural language processing deals with human language and some relevant problems like sentiment classification. So what this means is that I gives you a sentence. Can you tell me, does the sentence shows happiness or maybe sadness, something like that, right? Fraud detection, which is probably like what saves you from a bunch of spam emails. Text generation and language model, which is ChatGPT or all those language model that you use every single day. So you probably haven't, if you haven't heard the term NLP before, now you know what it is, and you're actually using it every single day, I suppose. So yeah, and one simple example is just gives an email. Is it a spam email or not? So you have to like read the content of the email basically. Yeah, and that's what me and I think Oscar's working on. So if you're interested in that, you can also talk to us. Next part, reinforcement learning. So reinforcement learning is more like what you usually do. It's just you learn from trial and errors. So some relevant problems are like self-driving cars, right? Robot learns to walk, AI learns to play chess, or like language model alignment, which is kind of irrelevant, but I still put it here. So one example is like AlphaGo, which hopefully you all know what it is, but kind of all reinforcement learning is doing is that let's say you play 10 rounds of chess and then you lose all 10 rounds, you say, oh, this is bad, and then I need to learn from what I did wrong in the past, right? So you have those, what we call experience, and then you can learn from those. So yeah. And you just like, after you play like probably a million games, you can be very good at chess. So that's one of the examples. And lastly, generative AI, which is something very interesting, hopefully. So it involves generating new data. So image generation, video generation, right? Text generation, those are all considered generative AI. And as an example, as you see the image, it's a AI generated image, which is pretty, pretty cool. So yeah, it's a very interesting field. So yeah, so if you want to like break into the fields that we talked about always before, MLF will provide you the very foundations and foundational knowledge and like practical experience to get started into those fields, because those are more advanced fields about the topics. Yeah. So now let's introduce some what we call the types of machine learning. So there are mainly three types. The first type is called supervised machine learning, which is what we'll be focusing on for MLF. So all it does is it learns from answers. So as an example, let's say you have an image, right, and it's a cat image. So what the label or answer means is just we tells the model that, oh, this is a cat image. So the model knows, and then they try to like kind of match it. So that's what we call supervised learning. And unsupervised learning is that you try to purely find the pattern in data without the answer. So, which is what like we won't be covering in this like series of workshops, but if you're interested in this, you can whether learn it yourself or talk to us later about it. And last thing is reinforcement learning, which is RL. We have a RL workshops coming very, very soon. So if you're interested in learning about RL, you can attend that. Yeah, I don't know why there's a line on the slides, but yeah, so types of machine learning problem. So there are a few types of machine learning problems. So first one is regression, which is what we'll be focusing on and what you learned today. So regression, as you can see on the image on the right, it's just there's a bunch of data points and you try to draw a line that tries to like fit the data you have. That's what we call regression. And in the end, your prediction should be something like a number, right? And classification, which is on the left image. So you have two types of data. Let's say the circles are representing cat images, and then the like cross are representing like the dogs images. So you're trying to draw a boundary between them to like kind of separate them, so you know which one is cat, which one is dog, right? Like if I give you a circle, then you know it's like a cat, something like that. And third is generation and fourth is control. Those are more advanced topics, which we'll not talk about. Yeah. So focus of today, we'll be doing linear regression, which is the simplest algorithms in machine learning. And you'll build your kind of first machine learning models today through coding. And yeah, so that's pretty much it.
Just go back over. Go back slide. So some of you might have heard of linear regression. So may I actually ask, who here has learned linear regression? That is a lot. Oh my goodness. But that's fine. So who actually knows like how the linear regression line is actually like calculated? So like for those who like know linear regression, right? What do you guys know about it, I guess?
Right, so. Perspectives of some values.
Yeah.
Right, such that it's to the square of the.
Yeah, so he basically summarized it. So I'll go over it in more detail afterwards. So yeah, that's very good. Thank you. So we'll start with this, right? This is totally real data. This is not fake at all. Let's say we have this data, right? I'm sure you already know the answer to this. So how can we approximate this set of data? Does anyone know how we can approximate this? Yeah.
By a line.
Yeah, by a line. Now, why do we want to approximate it with a line? So this is the core of machine learning, right? Let's say you have this graph here. Let's say you see a point that you've never seen before, right? So how are you actually going to be able to predict whether or not this person is actually going to land an internship? Well, you need some kind of function, or what we say, a model, to be able to make this prediction. So linear regression is what we're going to go over today. So who remembers this equation here? Now, who doesn't? Nice. I'm still gonna assume you know it. So when you learn about sorry, am I too loud by the way? I just need some feedback. Am I too loud here or no? Okay. So I'm sure you all learned what a linear function is. And you guys know it's y equals mx plus b, right? You know that is called you know the m is a slope, you know the b is an intercept, you know x is your input, right? But here in machine learning, we're going to change up some of the terminology. So with this linear expression, instead of using the slope m, we're going to use w. W is the weight of this linear function. The b, what you might know as y-intercepts, we're going to call it a bias. Well, the x is going to stay the same. So like I said before, this is probably the simplest version of a model. What it does is it makes a prediction based on new data. So let's say I had, I guess, somehow 1.5 MLF attendances, right? This model is going to be able to predict, okay, what's the percent chance you're going to land an internship? So now you might be thinking, right? If we have a lot, okay, wait, why is there this? How do you erase this? There's like a.
I actually have no idea. I don't know what's there. Is it actually on the slide?
No, it's always here. It's here. I got you. Sorry, there's like a random slit there after erase. There you go. Back to slideshow. Okay, so let's say I have a line, right? Now, is that line a good fit of our data? Yes or no? Why is that? Yeah, so the line is far away from the points. So now you might be thinking, well, I have a solution. Maybe tell me what you think about the solution, right? I'm gonna try every single line possible. Is that a good idea or no? Why is that not a good idea? Yeah. Yep, there's infinitely many lines. So it's very impractical for us to just go like, oh, I'm gonna try one line and I'm gonna go like this and like test every line possible, right? So then we need an indication of how good or bad this line is. Now I know that you over here already know what I guess the metric for this is, but we're gonna introduce it. It's called the mean square error loss. Now, may I know who here knows about mean square error loss? Raise your hand. Okay, some of you guys do, some of you guys don't, so that's great because I can introduce it here. So let's say I have that really bad line, right? And I want to actually be able to compare this line to the rest of the points. So how can we do that? Well, there's something called a mean square error function. So essentially, this tells you how far off each of the points are compared to that line. So the mathematical formula, you might understand it, you might not, but don't worry, we're not here to make things math heavy, right? All this math expression says is you take the difference between the data, like the data point you have, and whatever the model is predicting, you square them and you sum them, and you take the average. Is that clear for everyone? Does anyone have any questions about this? Okay, so if we have this mean square error functions, what do we actually do with it next? Well, like I said before, sorry. If you look at that formula, right? So y subscript I is the wait, hold on. Sorry. Okay, y subscript I is the data point you have. And you guys see the y subscript I with the hat on it? Right? That is the prediction that your model makes. So you guys know that we're trying to model this line. Well, sorry. You guys know the model is a linear function, right? So then in here, you will substitute the linear model back into the equation. So you get this. Is this clear to everyone? Is it clear that why we put wx plus b into here? Good? So what do we do? So like I said before, there's so many different lines possible, right? So of course we want to be able to get a line that really fits. And if you look at this equation, right? What can you actually control? Yes. Yeah, you can only change the value of W and B. Okay, now recall your calculus. I'm sure everyone is taking calculus here, right? So if that function tells me how bad the line is compared to my points, what do you want to do with it? So that your model is good. Yes? Yep, you want to minimize it. So our goal right now is to minimize the the mean square error. And we'll actually teach you how to code this at the end of near the end of the workshop. But right now, I'm just going over the theory. So if we look at the mean square error function, right? That was a quadratic to you, correct? That's a quadratic function, right? So let's say that is your mean square error function. Our objective is to minimize it. And we want to make the mean square error the minimum. We want to get to the minimum. But we need to think about how we can do that. Okay, not that. So we want to nudge the loss into that minimum over there. And right now, before I teach you how to actually minimize that, I'm going to introduce you to a little bit of more calculus. So this is called the gradient. The gradient is made from partial derivatives, and it gives you the direction at which the function increases the most. So this might look very scary, but don't worry. That first expression here, right? That is the partial derivative of the mean square error with respect to the weight. For the time being, you can just treat this as a regular derivative. Is this clear for everyone? Yep. The second one is the same thing. That is the partial derivative of the mean square error with respect to the bias. So why do we need these? Well, because this tells you, well, first of all, let me just quiz you guys. What does the derivative tell you? Yep, and what is the instantaneous rate of change? How would you actually explain this in simpler terms? What does it actually tell you?
Slope function.
Yep, but what is the slope actually telling you?
Points in like the pointer to a direction too. So yeah, I can go down.
Yep, precisely. We're gonna say that as well. Yeah. So that is what the derivative is, how steep the curve is, and more specifically, in this situation, right? If you are to get the derivative, that's gonna point you towards the minimum, and that's what we want to achieve in here. Yeah. This is nice one. Yeah, so this one might be trivial, right? So what we have here is a quadratic, and let's say the x-axis is the weight. You guys remember the weight from the line, right? The W, right? And I guess the vertical axis is the MSE. So if you take a small step in that direction of a derivative, your mean squared error loss is going to go up. So for it to go down, what do you have to do? Yes. Yep, take a negative of it. So that's exactly what's going to happen. So when you have your mean squared error function, right? You know how we put in our weight and the bias into it? What we have to do is to nudge those values such that our mean squared error are minimized. So like, I forgot who said, someone said to subtract from that derivative, right? So this is what's going to happen. We're going to have to use something called an update rule. This is very important in machine learning. Yeah. So we'll teach you how to systematically do this. For now, this is just theory for it. So what you do is, right? Let's say I have a mean squared error function. What you're going to do is you're going to take the partial derivative of the mean squared error with respect to these parameters to every single point you have, and you're going to do this update rule. Yep, so this is the algorithm. So for every point we have, we're going to take the partial derivative of the mean squared error with respect to the weight and bias. And then we're going to update the weight and bias based on this formula here. And we're going to keep repeating this until we're satisfied with the results. Now, can anyone foresee a problem with this approach? Yeah. Yep. So she said jumping too far. So what does she actually mean by jumping too far? Recall the goal, right? You see the ball up here? We're trying to drive that ball into the minimum. So how we're going to try to achieve this, right? Is by tweaking the weights and bias values. But what might happen? Well, first, I have to introduce you to something. I'm sure when you look at this formula, right? There is something I haven't introduced yet. What is it? The alpha. So what is this alpha? Well, if you're given a certain point, right? How much should we actually push that ball towards the minimum? That's what alpha is. That's what alpha is. And alpha is a parameter that we actually set. This is called a hyperparameter of our model. Now, what's actually going to happen? What could cause this ball to just keep jumping around? Well, if you nudge this ball too fast, right? Let's just think physically here, right? Let's say I'm trying to push the ball to the bottom of that curve. What if I push it too fast or hit it too hard? Well, this is going to happen. You're just going to keep bouncing around the mean squared error, and you might not actually converge to the minimum. Now, what if I push it too slow? If I push it too slow, I'm never going to get to that minimum, right? So a big part of machine learning is actually determining how much you should be, pushing this ball. And you need to do a lot of testing and tuning to be able to achieve that. Also, you might be thinking, right? If you look back at the MSE formula, you might be thinking, well, why can't we just use calculus and find the minimum of this? Why can't we just do that? Does anyone know the answer to that question? Yes. Yeah. Yeah. So the points are very, very scattered here. you're gonna be taking so many derivatives just to find the minimum. And there is one more problem with this approach. Right? So far, we've been looking at a normal line that you've been dealing with in the 2D plane, right? And if we go back to this graph here, how many variables does this function have? 2. Well, there's 2, but think about it. What if the percent chance that you'll land an internship depends on other things? What would you actually do? How are you going to be able to format this? Let's get here. So yeah, we're only looking at the one-dimensional case of linear regression. So the chances of landing internship only depends on your MLF attendances. So one variable. But the more variables you have, the harder it is to find the minimum. I'm sure we all know that. Now, don't worry, this is not a math and calculus course. You can experience the hardcore math in second year instead. But I need to conceptually understand this. Let's say I have a function that is this long, right? Let's say there's so many weights to this function, right? First of all, does anyone understand what that function up there is? Or can anyone tell me what that function up there could actually be telling you? Yeah. Is the what? Well, not really. So we talked about, we're trying to model something with a line, right? And you know that y is your output, right? But let's say your output depends on many other variables, right? And let's say you want to model them as a line as well, or linearly as well. That's how you would do it. And with the mean square loss function, if you go back to here, right? If you go back to the mean square error function, we're only looking at a singular weight and singular bias, correct? Does everyone agree? Well, if you have many variables in your function, you're going to do the exact same for every single weight and every single bias. Now, you can imagine why it's better to do this nudging instead of manually finding the minimum with calculus. Now, good news. I'm sure some of you might be a little confused about all the math that's happening, but you're going to do this through coding, which is the part that we're going to get into, and probably the most exciting part, because that's where you'll be able to build all your ML applications with. No one ever does this math by hand, unless you're taking APS 360, but I'm not here to defame that course. So PyTorch time. So everyone, please take out your laptops, and we'll set up a coding environment, and that's where you get most of your practical learning, and you realize that the slide will actually begin to make sense as you go. Yeah, what's up?
Yes. If there are more than one local minimum, the mean error in the loss function.
Yep, and that's what we're gonna try to find, right? If you go back to here, that curve can be like infinitely as much, right? The whole point of nudging it is so that you can try to like nudge it towards that direction. And that's why it's actually important sometimes that you can have jumps, right? Because let's say in that curve, you have another minimum down there. You actually want to jump out of that minimum so that you get to the other one. Does that make sense?
I wish I have a drawing. I don't see the drawing. Yeah, so I guess your question is that if there's like multiple minimum, like a wave, right? So what do you do with it? So in this case, there's something called the global minimum, right? And there's something called the local minimum that, as you probably learned in high school. So global minima is the global like smallest or minimum point of the function, right? And then local minima is just a like something like here, but if you can be like here, and then you have like a way deeper curve somewhere else, then you don't know about it because you think you're just stuck there. So this is one of the active research domain, because how you initialize your parameters in your neural network does has a significant impact on whether you can find a local minimum or a global minimum. But for our case, I guess you can just think of it as you can start at different places of the functions, and then you have a chance of finding the global minimum, if that makes sense. Right, does it make sense?
So it's more complicated, right?
Yeah, because what? Yeah, but like, because the thing is that, let's say you have a local minimum, like, let's say, x equals 1, right? And then you have a global, which is like close to negative infinity at like, let's say x equals 1,000, then you don't know there's a global minimum, so. Yeah, you have to have some like clever ways of finding it, which is more advanced research. Yeah, yeah.
Several.
Hmm?
What if several local meaning of the actually done?
Yeah, so, in this. Hmm?
If we converge to only one.
Yeah, so it will only converge to one, but the like the idea or the research is how do you find a better minimum than the one you generally have? So that's the research direction. That makes sense. Yeah.
This is the absolute.
Like which way do you mean for gradient descent? So there are some variations of gradient descent. Like this is the very simple, like the most simplest form. You only use the gradient or the like derivative at the point, right, of the function. So like if you heard of the terms like what's it called, like momentum or RMS. So those are like other ways of more optimized or more like intelligent way of calculating the gradient. And you can combine them, which is what probably you heard of Adam. So yeah, like you can, there are some other ways of optimizing the gradient or like optimizing the gradient calculations and make it more accurate. But in our case, this way is good enough. Right? Because this is the like essential idea of gradient descent. Are you all good? You want to talk about the, are there more? Just the. Okay, you want?
Yeah, I just want to wait. Are we doing the Twitch?
Yeah, sure. You want, wait, can you talk about the limitation?
Yeah.
Oh, do you want?
It's not yet.
Not yet?
Okay, okay. Wait,
While you set it up, okay. Oh, do you want me to? Okay. Yeah, so we're gonna get into the notebook. We'll show you how to do it first. But I just want to like give a shout out to the technical writing team. Because they basically help us compile like all these slides and they developed the notebook. So shout out to Isabel and Veronica on internal comms for these slides, and also shout out to Adam, which is the VP technical writing, for making the notebook. And yeah, I will get into making or getting the notebook.
I can type for you. Like you can just.
Yeah, so go to. Yeah, so we're just going to show steps of how to get into the platform, the IBM platform that we're using for our notebooks. So yeah, if everybody could take out their laptops and click into cognitive class .ai right here. Yeah, maybe give you like 10 seconds.
Yeah, just search up cognitive AI and you'll see this.
Yeah, and then once you're in, then can search up machine learning fundamentals.
Is everyone able to find a website, by the way?
Yeah, is everybody good so far? Okay.
Is everybody able to get to here as well and find UTMIST?
Okay.
Okay.
Yeah. Okay, just keep going. Okay, yeah, and once you're here, click into machine learning fundamentals. Wait. Yeah, and then once you're in, you have to register. So maybe
But it got cut off for the
oh, they got cut out.
slightly. What should I do?
I just type in cognitive class.ai.
Yeah. I'll just send you guys the link.
But yeah, once you're in here, you'll need to register. So I think like you could just register with the Google account and that should work.
Yeah, just tell the online people that they can use register.
Yeah, online, for people online, you can use the link that Aaron just sent in the chat to register.
This is my email right here.
Okay.
It's okay.
How is everybody doing, by the way? Were we able to like register and then kind of like get into like where the chat is? Like, you might want to move it. Yeah. But is everybody able to like get here? Yeah.
Yeah.
Okay. Yeah, so just click register. We'll just let it log in.
Skip it now.
Yeah, so once you're in here, just click on start course. And it should be able to launch what we need. Yeah, so launch your project once you're in here. Is everybody still good? Yeah. Okay.
Is everyone on this page? Is everyone able to get in here?
Oh. Okay.
Yeah, click. Okay. Yeah, let's you run. I'll use some turn on this. Let's see.
Run the cell first, right, for installation.
For sure. Sure.
Um, yeah, so can we get a raise of hand if you're on this page where you're like at least on the loading page? Okay, we'll just give one like 1 minute more to like get to this page before. Okay, so hopefully everyone's able to get to this page. And what we'll need to do right now is we'll need to install some dependencies. So what you do is you click on the first cell here. Hopefully you can see on my screen. And then you click run, so it's the start button on the very top of the page. So you click on it, and then it will start executing. So it will see like that it will start downloading something, and it will take a while to download everything. So if you're able to get to this page, we'll take a 5-minute breaks, and you can go to washroom or talk to people or whatever, and we'll come back afterwards. And please raise your hand if you have questions about the platform or downloading dependencies or anything else. So, but if you're good, we'll just take a break, and we'll come back around like 2:18. So. The chassis.
Yeah, sorry, you want to like the screen bit because like, it's really hard to see with like switches just click.
Oh, zoomed in because it's got cut off on the.
Yeah, I got
Okay,
cut off.
they can't really.
Wait, there's a solution to this. I think we can solve it. Okay. Oh no, yeah, I tried GPT this. Aspect ratio mismatch.
What do I do?
Optimize for full screen platform.
Yeah. Do you want me to do that?
Do you want to explain like the Jupyter notebooks?
Yeah, I can do that.
Yeah, sure.
I just called him to. But you just called him to. Guys, we'll be kind of starting and yeah.
So I think most of your guys' notebooks have almost completed installation. At least I looked at like around half of the people had their installations done. But like maybe the other half still haven't had their done yet. So I'll just give like a quick explanation for what this platform is and some cool features to it that you might find useful. So this is a Jupyter notebook. Of course, this is hosted on IBM's platform. But there are other platforms like Google Colab, as well as local platforms like IntelliJ and VS Code, where you can also run Jupyter notebooks. It's a pretty standardized way of running machine learning scripts and stuff. It's just also great for learning because you can include a lot of these little cells here for explanations and stuff. So essentially what we did in this first cell was do a bunch of installs. So we're installing PyTorch. PyTorch is one of the forefront machine learning libraries, and it's really useful because a bunch of really, really smart people came up with some really good functions that we can use to do some of the things that they were talking about earlier with learning and training and stuff, which we'll get to shortly. But I'll just talk about the platform that we have specifically and a few features that you guys might find pretty useful. So essentially, when you run cells, there's a few ways you can do it. You can press this button over here, or you can press Shift and Enter. So if you click on the cell, you see the cell is highlighted. You can press Shift Enter, and it'll run the cell. You'll see that when we run cells, there's a star when the cell is running, and when there's a number, that means the cell has completed running. So those are just some Jupyter Notebook specific things. But one specific thing to this platform is the fact that we have access to some generative AI to augment our learning. So specifically, if you look up here, there's this thing called Ask Ty. If at any point you're stuck with something, if there's an error that shows up, there's this LLM that you can ask, you can prompt it, you can say, hey, there's a specific error that showed up. Can you help me fix it? Though we have, rigorously tested the notebook, so you shouldn't really encounter those. But if you do, first course of action would be to ask the chatbot. And then the second thing you could do is ask one of us, and we'll be glad to help you. The other thing is, if you're conceptually struggling with one of the concepts, if, of course, we're going to explain it throughout the session, but if at any point, like a line of code wasn't making sense to you, you just wanted a bit more, information about it, you can ask the LLM what a specific line is doing in the code, and it'll help you out. So yeah, just make sure to look up here for Ask Ty. But with that, I think that's pretty much an intro to Jupyter Lab. Another issue that might come up, not very frequently, is something to do with your kernel. So every single time, if you encounter some errors, I think there's like a sequence of things that you should do. First thing you should do is restart the kernel. It's not that like deep. Like you can just rerun things and it's pretty fast at that point. You don't have to it's not going to get rid of your libraries that you've installed. So that's the first thing. Second thing, you should ask the LLM. And the third thing, you can ask one of us. But yeah, I think that's a quick rundown. Any questions? No hands, so I'll assume there are none. With that, I'll leave it to Aaron.
Yeah, so let's just do some coding then. Hopefully your guys' installation is done. If not, you'll have just to leave it there and then watch my screen for now, unfortunately. But if your installation is done, you can kind of follow along, which is good. So, but hopefully you guys can large enough for you to see.
Yeah.
So first we'll do some introductions about PyTorch. PyTorch is a library built specifically for deep learning that uses Python, right? So yeah, that uses Python. So as you can see, the first thing we have is called tensor. So tensor is a specialized data structure that's designed for deep learning, but all it does is just whether it's, you can think of it as an array or a very high dimensional array. So let's say you have a 2D array or a 3D array or even higher dimension arrays. So here that you can run the cells and then you can see that, so you'll have multiple types of tensors. So first you have a zero-dimensional tensor, which is just a number. So you can see here, you have a scalar tensor and says 3.14, right? So you can just think of it as a number no matter what. And for a second, you'll have a 1D tensor, which is more like a array, right? If you're familiar with Python, and you can see you have a tensor of 1, 2, 3, and it's just like an array and nothing else. And also you see that generalized to 2D, which is a matrix, right? So if you print it, you see 1, 2, 3, and then 4, 5, 6. So it's 2 by 3 matrix. Yeah, so and you can do some basic tensor operations. So let's say here I created a tensor called x and a tensor called y, and then I can do plus. So in this case, since the tensors are the same dimension, they'll do element-wise operations. So what it means is that it will match the zeros index to the zeros index of the other tensor. So in this case, if I do x plus y, what it will think as is they will look at the first index of the first tensor x, right? And it's 10. And the first index of the y tensor is 4. So they'll add them together. And then as you see here, you get 14. And same for the first index. You have 20 in one and then 5 in the other. So they'll add them together and get 25. So that's what we call element-wise operation tensors. And similar for x times y, then hopefully it's pretty intuitive. What you will get is just you have 4 here and you have 10 here, right? So you times them together and then you get 40 as you print it here. And similar for 5 and 20 and 3 and 30 and 6. And also there's a function that works specifically for dot product. So in this case, we still use x and y. And if you want to calculate the dot product between them, you can just use torch dot dot, and then you input 2 of your tensors or you can just think of as like 2 vectors, and they will compute the dot products for you, which in this case is 320, right? And then you can also do the you can also try to find the main value of the function of a tensor. So in this case, you can do x dot main, which is also built-in function, and it will calculate the average of 4, 5, and 6, which is yeah. Okay. So yeah, the next thing we'll do is autograph. So as we discussed before, that in order to find the minimum, you'll need to find the gradient, right? Which is kind of annoying if you have to do that manually. So luckily, PyTorch has a specialized library called autograph that computes the gradient for you. So we'll just like take a look and look at like what it does, but in general, it's pretty easy to do. So in this case, let's say you have a function, right? Y equals x squared. And so it's pretty easy that your derivative of this function is just dy dx, which equals 2x. And let's say we're at x equals to 2, right? So your derivative at this point is just you substituting x into the derivative, and you get 2 times 2 equals 4. So let's see how this works in PyTorch. So first, you define a tensor x, and the value has 2. In this case, you put 2.0 because in general, we do want a floating point number instead of an integer. But that's a more detailed thing. And then you need to put requires graph equals true. So what it does is that it tells PyTorch to keep track of the gradient of this tensor. Okay, so now you have this two tensor, and you need to define the function of y. So y equals just x squared, so which is pretty simple. And in order to tell PyTorch to compute the gradient, you do something called y dot backward, and this tells the PyTorch to like compute the gradient for you, which in this case it says compute dy dx. And when you print, you can access the gradient of this tensor through x dot graph. So it tells you to access the gradient, and you see if you run the cell, you will get a tensor of 4 because that's exactly the gradient we computed. Yeah, so that's how you get the gradient of a tensor. And so now let's see a case that if you have two variables, right, or a tensor of like 2 dimension, not 2 dimension, but like you have like 2 elements in the tensor, so x1 and x2. So let's define a function, something like y equals x squared plus x1 squared plus x2 squared, right? And if you know the partial derivatives, dy dx1 is just equals to 2x1 because you just ignores the x2 part. And similar for dy dx2, it just equals to 2x2, right? Which is pretty similar to this case. But anyways, so you have your derivatives. And let's say we try to evaluate x1, the derivative of x1 at x1 equals to 2 and x2 equals to 3. Then still it's pretty easy. You just substitute in those numbers and you get dy dx1 equals 4, right? And dy dx2 equals 6. So these are your gradients, which from a theoretical point of view. And so here, similarly, we do something like before. You have torch.tensor, you create a tensor of 2 and 3, right? And you create requires graph equals to true. And then you define a y functions. So in this case, as I said, it's an element of y's operation. So what it does is if you do x to the power of 2, it will take the power of this element, takes the power of 2 and takes the power of 3 individually, right? And you use a dot sum function, which just tells you, oh, like my tensor has 2 elements now, you add them up. So this is like these 2 lines are just exactly how we define this function of y equals x1 squared plus x2 squared. And now you need to compute the gradient. So you tell us, y dot backward. So you tell us PyTorch to compute the gradient for you. And if you print it, you see you get a gradient that's exactly what we calculated, which is 4 and 6. So now you have a small things to think about. So what if I do, and so here, right, I did y equals x to the power of 2 and dot sum. So what if we do y equals x to the power of 2 dot main? Then what would like the main value of this? Then what would the expected gradient to be? Yeah, does anyone know? You know what? You know what? Like, can you explain to everyone why is that supposed? Yeah. Yeah. So in this case, if I do print, okay, print x dot graph, right? So if you want to see, you'll see 2 and 3. Why is that the case? Because instead of taking the sum, we take the main value of this between these 2 elements, right? So what the original function would look like here is that you have a function, something like y equals x1 squared plus x2 squared, and you try to take the main value. So there are 2 elements here, so you try to divide it by 2. So that's why your gradient is also divided by 2 compared to the previous operation. So does that make sense so far? Okay, I'll take that as a yes. So yeah, now let's talk about how you do some basic training with PyTorch. So first of all, you should prepare the data, right? That's be done through data loaders, and you need to define a model, which is in our case is well, you need to initialize a random line. That kind of doesn't really fit the data, but you need a starting point to like let the line gradually fit towards the data. Right, and you need to define a loss function, and this is what we talked about before, which is the mean squared error loss. Hopefully you still remember what it looks like, but we'll have the formula later as well. And you need to define the optimizer. In this case, could have SGD or Atom, but these are more advanced topics, so we won't really talk about that today. But just remember you need that, and you need to build a training loop. So with a training loop, it's just it will iterate over the data and then tries to adjust the weight and the biases of the model gradually. So yeah, you don't have to worry about all these details right now. You can take a look later yourself, but we'll just do a quick demo of this. So as we learned today for linear regression, the formula is y equals wx plus b, right? So in this case, let's have a problem or let's generate a data set. You don't have to worry about where this comes from, but you'll see that, let's say we have a data of the number of hours you studied and the score you get on one of your exams, right? So it makes intuitive sense that maybe you study longer, you'll get in generally like get higher score, right? So you see a positive correlation between the two variables, which is your exam scores and the number of hours you're studying. And like we generate this data just using a line, and the true line is y equals 5 times x plus 50. So if you study longer, you will get higher score. And let's say if you study, in this case, if x equals 10, you're supposed to get like around 100 or something. But we also added a noise to it. So your data is more like not just like purely a line, it will like have some fluctuation. Yeah. So now hopefully you still remembers the linear regression formula. Loss function, which is the mean square error. So you have 1 divided by n. N is the number of your training examples, right? And you try to take the sum of all the differences between your ground truth and your predicted value. So in this case, your predicted value is y hat, and your ground truth is y of I, which is the subscript I just the superscript I just refers to one training example, and you take the square. So you make sure your loss is positive. And similarly, you've seen this gradient descent update already. So you update your weights by taking the partial derivatives of your loss function with respect to your weights and also biases. And you also times a what's it called? Learning rate or step size parameter, whatever you want to call it. So yeah, here you have the loss formula. I think we've seen this before, but now we just expanded it. So yeah, we don't have to talk more details about that. So now let's do a manual gradient computation, which is the exercise. So I guess all you need to do is that you will need to fill in the I have the answer here. Okay. So yeah, so I'll give everyone like 3 minutes to try to compute the gradient for W and B. Not manually, but like in code. So you'll get a better sense of like how those things works. Wait, doesn't that mean everyone else has the answer?
I don't know, I'm checking right now.
Okay. Okay. That's funny. Okay.
I guess like you want to solve.
I guess they already saw it. But also, no, I can just receive.
Just say like, maybe this is the to-do.
Oh, yeah,
You just wanna like highlight this.
sure.
Okay.
But they already see the answer. There's no point.
Yeah, that's fine.
Okay, I guess there's a small technical error that we actually accidentally like put the answers there. But technically you should do is you put your formulas here if you want to do it yourself. Like instead of in the training. Okay. Okay. Anyways, let's come back together and then see how we do this gradient computation manually. So remember you have the formula here, right? Which shows the gradient, which equals to 2 divided by n, and the sum of the differences between your ground truth label and your predicted value, right? So here then, wait, where is it? Yeah, so here, if you wanted, in this case, let's just do these things manually. So for the gradient of W, you want to do 2 times, right? And divide by the number of training example. And in this case, it's just the hours, the element, or you can just do n because we already defined the variable of n up there. Like, hello. Hello. Why my notebook is gone? Okay, anyways. Yeah, my notebook is somehow gone. So I'll just do hours the element. In this case, num-L. So num-L just tells the number of elements within that array or tensor, right? So which is in the formula, it refers to this n, or here n. And now you want to do some summation, right? So you can do that through torch. Oh, you have to type like torch dot sum. And right, so what do you need to sum? In this case, for the weight, you need to sum, here's your predicted value, right? Minus your ground truth value. So your predicted value is just what's here before computed called the error term. Or no. Wait. So you have an error term. And what you do is that you times the hour, because hour is in this case, hour in this case is your ground truth value. So, or no, it's your x value. So you want to times this. And this term in the middle term is what we call the error term. So it's just what we computed before, but my notebook is gone somehow, so I can't really show you guys that. Anyways, so similarly for the biases, you can just copy this because it's pretty similar, right? So you remove the non-value. And as you can see, the formula, you just don't have to times you just have to remove the xi in this case. So you don't have to times the hours, which is your feature. So you only have the error term. But anyways, you should have something like this, which is what we show as the answers to the gradient computation. And then you can just run it, and then it will train a model for you, small model for you. So as you can see, epochs is the number of training loops. So we're like one update to the model's weight is called one epoch. And what we did is we update the model's weight 1,000 epochs in this case. And you can see we printed the loss. So as we said, the goal of gradient descent is to minimize your loss, right? So at epoch 0, your loss are at 6,370, which is pretty high. And as you can see, through each epoch, our loss is gradually decreasing. It decreased very fast at first, and then it kind of gradually converges to a value which seems to be like 16 or something, right? And when we print the model's parameter, you have a learned weight of 4.8, and you have a learned bias of 50.7. So if you recall, our original formula is the weight is actually, the true weight is 5, and then the true bias is 50. So we learned something pretty similar, which is good, right? And let's just see how the results works on the what our line looks like. So, hello. Oh, there's 5%. Yeah, so you see, the red line is the model we learned, and has a very, very good prediction of, or what's it called, model of the data, right? And you can see your training loss is also decreasing as expected. So good. And we can also, well, you probably said that doing the gradient option, like gradient computation manually, is very annoying. So PyTorch actually has something that does it for you, and it's called the n.linear layer. So it would generate a like linear model for you instead of you have to do everything yourself. So in this case, if you do n.linear and you specify, in this case, 1 and 1, these are called the input features and output features. We'll dive more details into it, but you can think of the input feature as just whatever you input in this case, which is just the number of hours you study, right? And then your output feature is, in this case, also just your output, which is the exam score you get. So hopefully it's pretty intuitive. And then you can also define a loss function. In this case, we use the mean square error, which is MSE. So you just defines a n.mse loss, which is also built into PyTorch. So you don't have to write everything yourself. And here you have an optimizer. Optimizer just does the gradient update for you, but you don't have to worry too much about it. And there's also something called SGD, which we will dive into in the next few weeks. So, but for now, you can just think of like with these 3 lines, it does everything for you, and then you don't have to do too much more. So you also have here your training loop. So we also runs 1,000 epochs. And all you need to do is you found a loss equals the loss functions, right? And you input the ypred, which is your predicted value by your model, and ytrain, so which is your ground truth label. And then it will calculate the loss for you. And you do optimize.0grad, you probably don't need to know what it is right now. And loss step backward, as we see before, this computes the gradient for you, right? And optimizer.step, it just tells the optimizer to update the gradient for you. So loss step backward computes the gradient, and optimizer.step calculates the gradient. Update the gradient, sorry. So if we run the training loop, which you'll see, what? Module not found. What? What? You told stop pi. No, I never run to this.
It's
Interesting. I don't know. I guess we can just proceed then. Because I can't do it. Oh. Yeah, so it seems like people are running into the issue about modules not found. Can we get raise of hand who got this issue? Okay, quite a bit. Did anyone doesn't have this module now found issue, so you can run everything like normally? No? Okay. So what's the issue?
You just have to restart the car. I don't know why that's happening.
Does that mean they have to reinstall?
No, that is after you install it, like all the packages are already kept in your kernel.
Oh, okay. So they said you have to reinstall your, no, restart your kernel. So if you can try that, where's the button? Here.
Yeah.
So yeah, so,
This one.
oh, yeah, so if you see this restart button, you can just try click it and it will restart your kernel. And you can try run the code again and see if it still gets this issue.
One more thing, after you reinstall, like you don't have to do the pip install part again, but you have to start running from the first cell because you have to import torch again.
Oh, okay.
Yeah.
And after you reinstall, you don't have to rerun in this cell, you don't have to run it again, okay? You can just start running from here, so from the first.
Cell. Line.
But anyways, I guess just for time concerns, that while everyone's trying to restart your kernel, we'll just keep going. But as we said, in this case, you define a model which is using the PyTorch built-in functions, which is a lot easier, and then it doesn't, like, you don't have to do all the gradients computation and derivatives manually. So in this case, you see we also get a model which is pretty much the exact same as before. And if we plot this, what we learned, it's also the same graph. So all it says is that PyTorch has something built in for you, and then you can just skip all the painful gradient computations part, which is very good, hopefully. Yeah, that's pretty, yeah. Oh, sorry. This.
First box, the equation can be lost for a couple and it's started.
Yeah.
The C lost a lot,
Yeah.
Why? That's like what's going on, why is it?
Because remember your formula here. Here, can you look at this part, right? So your gradient is computed by the differences between your predicted values and the actual values, right? So for the model, we first randomly initialize a line, right? Which can be very bad. So you can predict, like, let's say the actual number is like 100, like actual score is 100, but you can predict like negative 100, which is very far away. So in this case, the difference, the inner term, the difference will be very large. So that's why you did a very big update, because the difference between your true value and the predicted value is 200. So you will have a very, very large gradient update because the model is very bad. So as the model getting better and better, your error terms get smaller and smaller, so you'll get smaller updates. So that's why you see the loss function flattens as you're training your model, because it's getting better and better. Does that make sense? Yeah.
This usually was a very idealized case, so how could you get to this was initially very idealized case. You utilize like one outside.
So his question was that our line or our weights learned is from like your weight learned here is 4.8 and your bias learned is 50.7, which is a little bit different from the actual equation, right? Because in this case we used 5 and 50 as weights and biases. So and his question is that why is it different and can we learn things perfectly? The answer is unfortunately no, because we generate the data in a noisy way, right? So you see your data isn't like perfectly aligned. So there's no way you find a line that perfectly reconstruct these data. And these data are constructed randomly with added noise with some standard deviations and into it. So that's why you get a noisy approximation for your line, because your data is noisy, which is true for any real world data, right? Because you can't have a perfect line in any real world data. There will always be outliers and stuff.
When practice is all considered good estimation.
Good estimation.
Yeah, you never have from license, real life comparison.
Yeah, so there are certain evaluation matrix, right? So in this case, you can see that, in this case, I guess it's very subjective because let's say I study for 8 hours, right? My exam score should be like, let's say 90, right? Following this formula. If my prediction is saying 89, well, I consider that to be a pretty good approximation, right? In this case, it's just more subjective. But for other tasks, like let's say for classification, you can have something called accuracy, which hopefully you know what it means. Right? I think everyone knows what it is. But like accuracy is see how much images you correctly classified and were misclassified. So, but how much are you like considering it to be a good, very accurate model? I think that depends, very task dependent and depending on like what you want to use the model to be. So for some tasks, you might have like a 60% accuracy and you consider that's pretty good. And for some other tasks, you need like a 99.9% accuracy. So it's very subjective. But in terms of evaluation, we do have other tasks, we do have other methods, something called F1 score or all those stuff that we'll introduce in week 7, I think. So yeah. I'm done. I'm done. Yeah, so there's a question from online. Hopefully you can hear me. What parameter is determining how much we are nudging? So what determines is this alpha term. The alpha term is the learning rate of your model, right? So if you have a very small model, then your gradient update will be very, very small every single time. And if you have very large alpha, then it will just update a very large gradient. In general, we want to keep alpha to the smaller side because it will make sure we don't get something like the jumping, which is what we showed on the slide, like here. So you want to prevent this situation. So you kind of, in general, you want to use a smaller value of alpha to start and to make sure your model converges. Hopefully that answers your question. Okay, so I guess just to wrap things up, since we're almost run out of time. So we learned linear regressions today. And the limitations of this model is that, first of all, many problems are not linear, right? So there's not necessarily a correlation, just positive or linear correlation between two variables. So what you can do in this case, you can use something called linear regression, but we're not gonna or polynomial regression. But in this case, we're not gonna introduce it. So if you're interested, you can talk to us afterward. And also there are outliers, right? So in this case, as Warwick made on slide, so the correlation between you landing an internship and how much lessons you attend for MLF is not really directly correlated. And there are other factors like how many LeetCode questions you do, or your GPA, so all those stuff. So there will always be outlier, and you can't really I guess perfectly predict anything, because there will also always be something that you don't expect that happens. And what does it mean to be very shallow? I don't know. What does it mean to be very shallow?
Yeah, I got it.
Okay.
Yeah, so the very shallow part just means it doesn't take into consideration enough patterns, right? It just immediately assumes a linear pattern. Like even if those dots represent like a quadratic function, linear regression in that case already fails. But that's fine, because we're going to introduce you to even more complex algorithms in the next few workshops. Yeah. So that's kind of it for the first workshop. Hope everyone had a great time. I know it's a simple algorithm, but don't worry, we'll get into even more technical details and more interesting algorithms in the next few workshops. So hope everyone enjoyed it. Thank you so much for coming.